It's 6 p.m. Friday. The dinner rush has hit, the kitchen is at maximum capacity, and speed is the only metric that matters. Then, directly above the ordering register, a critical digital menu board goes black. The line halts. Customers stare at a blank screen, and the floor staff scramble to find someone who knows how to fix it. Floor managers often assume these blackouts are random glitches, the kind of bad luck that comes with running high-tech equipment in a busy kitchen. In reality, a crashed screen in a commercial environment is a predictable event. A black screen is a silent revenue leak. It immediately drains check averages because customers can't see high-margin upsells, and it erodes the brand trust you've spent years building. Most digital signage systems perform flawlessly in a controlled IT demo, but when subjected to 24/7 strain in a production environment, standard configurations begin to fail. Achieving high reliability in these settings requires a specific set of physical and digital constraints that go beyond basic software settings. To understand why, we will examine the internal hardware and software stressors that cause a unit to collapse. We will then look at the 3-layer prevention stack used to harden a deployment against those specific stressors. Finally, we'll detail the automated recovery posture needed to handle the edge case failures that no amount of hardening can prevent. The goal is to move past the idea of a system that never fails, and instead engineer an environment that acknowledges reality and recovers instantly. To see what happened, we must look inside this media player, mounted tightly in an unventilated wall cabinet. Unlike office computers, commercial menu boards often run for weeks without a single restart. When you add kitchen grease and restricted airflow, the ambient temperature inside that cabinet climbs until the CPU reaches its thermal limit. The hardware attempts to protect itself through thermal throttling, intentionally slowing processing tasks to generate less heat. Eventually, the internal temperature exceeds a critical safety threshold. The system performs a hard shutdown to prevent the components from melting, causing the sudden blackout on the floor. Physical degradation is another factor. Inexpensive consumer-grade SD cards aren't rated for the continuous read and write cycles of a commercial media player, leading to storage failure. Hardware in these environments rarely fails from old age. It usually fails because it is suffocated by the harsh conditions where it operates. Where physical heat ends, digital exhaustion begins. This gauge tracks the RAM capacity inside a standard media player. Many crashes are caused by a memory leak within the application. This happens when an application plays content, but fails to release that memory back to the system once the file finishes. Every new file pushes the gauge slightly upward. After days of operation, the available memory reaches zero. The application locks up, and the menu board freezes on a single frame. Network dependency adds a final risk. Pulling content live from the cloud means a dropped internet connection instantly crashes the entire player. When you combine heat, memory exhaustion, and network instability, a frozen screen isn't a random event, it's a predictable system collapse. Preventing these failures requires a 3-layered approach: hardening the hardware, stabilizing the software, and building network resilience. Layer 1 is hardware hardening. Use active cooling fans to maintain constant airflow. You also need to specify enterprise-grade storage components and dedicated surge protection to prevent data corruption during power spikes. Layer 2 focuses on software. By scheduling automated restarts during off hours, you reset the system and clear any accumulated memory leaks back to zero. This layer also includes content validation. Testing every file on a staging player ensures unoptimized media won't crash the system once published. Layer 3 is network resilience. Through local caching, the media player stores content on its own drive, so the display runs even if the internet fails. We also employ graceful degradation. If a live data feed for a menu item fails, the system automatically falls back to a cached static image. Reliability in these environments isn't about hoping the software is perfect. It is about maintaining a rigid operational checklist. No matter how much you harden the stack, unpredictable edge case crashes will still happen. This is why the most important metric for an operator isn't just uptime, it's the mean time to recovery. This timeline compares a traditional IT setup on the left with a resilient system on the right. On the left, a crash requires manual discovery, a call to IT, and a long wait for a reboot, while revenue bleeds. The right side utilizes Watchdog services, independent processes that monitor application health. When a fault is detected, it instantly triggers an automated power cycle. The Watchdog kills the frozen application and restarts it automatically. The screen is back online in 30 seconds, often before staff even notice. True operational resilience comes from this kind of automated self-healing. There are rare instances where a total hardware-level lockup prevents even the Watchdog from executing a reboot. In these cases, store staff should follow a first 60 seconds protocol, prioritizing immediate manual recovery. This schematic identifies the most critical physical information on the floor, the exact location of the hidden power switch used to force a hard cycle. If a hard reboot fails, the team follows a 4-tier escalation path, from the store manager to remote IT, then to vendor support, and finally an on-site technician. By diagnosing the environmental stressors, armoring your deployment, and engineering for automated recovery, you take control of your uptime. A display that crashes and autonomously recovers in 30 seconds is far more valuable than a pristine system that takes 3